Hi guys, my name is Louis Jeffrey, you can call me Jeffrey. So my lecturer is Dr. Hashida. So today I will talk about fin equation. It's normally we are deriving a force situation of the the boundary condition. So first of all, what is the fins? Fins is a shark fins, plant fins, or shark fin soup. No, today the fins we're talking about is the electronic fins that will reduce the heat from the devices. Okay, introduction of the fin equation. The energy, this is the energy balance, which is the rate of heat conduction into the element X equal to rate of conduction of the heat at the element X plus delta X and the rate of heat of convection. Okay, so first is the general equation from the equation. Okay, the second is the Fourier law of heat conduction, and the third is the convection formulas. So first of all, we sub the equation 3 into equation 1. So we get the equation and divide by delta t. So we obtain, and the delta t is approximately to 0. So we obtain the equation of 4. After we obtain the equation of 4, we sub the equation of 2 into it, and we form the new equation. After we form the new equation, we'll get dt over dx ka dt over dx minus hp bracket t minus t infinity bracket equals 0. So because the k is equal to constant, so we can bring it forward. So we divide by ka, so we get this equation 5. After that, we sub the equation of this number 6, number 7, and number 8. This is a general equation, which is the delta equal to t minus t infinity, and dt over dx equal to d delta over dx, and d square over hash d square equal to hash p over ka. So we can form this general equation, and we integrate it. We can get this formula where this is a general equation we will use. After this, we derive the equation. Okay, so the type of the boundary condition of fins got 4 types. The first type is infinitely long fins. Then the second type is negligible heat loss from the fin tips. Then I will talk next in the next slide. So the specific temperature, convection from the fin tip. So first of all, we're talking about the infinite long fins. The boundary condition is delta L is equal to TL minus T infinity equal to 0, and L is 10 to infinity. First of all, we need to find out the value of C1 and C2, where C1 value is equal to 0 and C2 is equal to delta B. So after we getting the C1 and C2 values, then we can solve the equation of delta x. After we find out the equation of delta x, we can find out the equation of dx, and then from the dx equation we differentiate it, and we sub into the Fourier laws of heat conduction equation, and we get the rate of conduction of the long fin, where is equal to Tb minus T infinity multiplied by square root hp ka. Next, we talk about the negligible heat loss from the fin tips, which also we call it adiabatic fin tip. So its boundary condition is delta t delta over dx is equal to 0, where x is equal to L. So first of all, we need to find out the value of C1 and value of C2, and after we get the value of C1 and value of C2, we can find out the value of delta x. After we find out the delta x equation, we want to find the tx equation, then to find the differentiation of the tx equation, which we can sub into the Fourier law of conduction equation. So in order to find the rate of conduction of adiabatic fins, so we just sub the equation into it, and sub the m equal to square root hb over ka. So we can find out the rate of adiabatic Finn's equation is equal to square root hb ka bracket tb minus t infinity tangent ml. The third case is specified temperature, which the boundary condition of it is theta L equal to TL minus T infinity equal to theta L, and then this is a normal origin theta. So first of all, we find out C1 and C2. Okay, after we find out the C1 and C2, okay, we need to find out the theta x. We only substitute the value, then we find out the theta x, and then after we find out the theta x, we can find the Tx formula. Then we find out the Tx formula, we can get the differentiation of the Tx equation. Okay, from the integration of Tx equation, we substitute into the Fourier law of conduction equation. So we get the rate of specific temperature conduction rate, so which is equal to square root of hb ka bracket tb minus t infinity cos ml extra k evaluation. Okay, the last is the convection of from the fins, which the boundary condition is equal to negative ka dt dx, where x is equal to L and equal to ha TL minus T infinity, and the original theta is the same and as the other. So first of all, we need to find out the C value and the C1 value and C2 value. So after we getting the C2 and C1 value, we can get the theta x value. Okay, from the theta x value, okay, we can get the value of Tx equation. Then we differentiate, getting the equation of differentiate. After we find out the differentiate Tx equation, so we just substitute into the Fourier law of heat conduction equation to find out the rate of conduction of convection equation. So we substitute it and we factorize it, and we find out is equal to square root of hb kx bracket tb minus t infinity shin mx h over km cos mx cos ml hash km sin ml, and this is the general equation of the four, and then this is the ways how I derive it. Okay, do you all understand? No?